Alright guys, so in this video we are going to be talking about modeling harmonic motion with sine and cosine functions. And we're going to say that harmonic motion is a periodic oscillating between extremes about an equilibrium. So we're talking about the motion of an object that goes back and forth across an equilibrium to extremes that are equidistant from that equilibrium. Right? In general, we can see how the sine and cosine wave would help us model this kind of motion if we let the x-axis be the time axis and say that the height and the depth of the wave is going to be the distance of the object about the equilibrium or the center of the wave. In general, right here, what we're going to be talking about is objects that are oscillating in time periods that are not in terms of units of pi. So a big trick to this is going to be determining the b values that we multiply inside the function to take our cycle and alter it to a length that is going to be in terms of units instead of units of pi. So right here, we've got two ways of doing that. One way is that we're given the period length, the time period that it takes for us to go through an entire cycle right off the bat. And if that's the case, then we can basically say that we know a period is 2 pi over b, and so we can just solve for that b value. So if we're looking at an oscillating motion, right, a harmonic motion, that let's say sees a full cycle in a period of, let's say, 4 seconds, right? So right here, what we could do to determine the b value is set that 4 seconds equal to 2 pi over b, and then solve for the b that we would need in order to see that cycle happen in 4 seconds, right? The second way that we're going to talk about determining that b value is with what we call frequency. And frequency, in general, is going to be the number of cycles that we get through in a particular length of time, or length of units on the x-axis. Right here, we've looked at frequency with regards to a full rotation, 0 to 2 pi previously. There we said that frequency was just going to be the b value. Right here, if we're looking at y equals sine of 2x, we can say that we have a period of pi. And we can see that we get through 2 full cycles in a length of 2 pi on the x-axis. Right? But the frequency that we're going to talk about more specifically is going to be frequency with regards to a unit length, or a length of 1. And right here, we're going to say that that frequency can be determined by taking the b value and dividing it by 2 pi. Now, right here, we know that we have a period of pi, right? And in general, right here, what we're looking to do is to see how many, or what portion of a period we get through in a length of 1 on the x-axis, right? So right here, one way we could think about this is basically if we were to take a length of 1 and see how many lengths of pi we could fit into that length of 1, and that would give us our frequency. Now right here, that turns out to be approximately 0.3183, right? So right here, if we look at an entire cycle going all the way out to pi, or approximately 3.14, we can basically see that this length of 1 is almost a third of that entire length, right? Maybe a little bit less than a third of that entire length, right? Which is what we're seeing right here when we take our period and divide 1 by that period length. We're saying that we get through 0.3183 of an entire cycle. Now right here, if we were to use our formula, we're basically going to see that same number, where if we take the b value here of 2 and plug it in, we can say that we've got 2 over 2 pi, and right here that would give us 1 over pi, or that 0.3183 as the frequency, or the number of cycles, or parts of a cycle that we get through in the length of 1 unit, or from 0 to 1. Now right here, in general, what we're going to see from these harmonic motions is either the period length given to us in the problem, or we're going to be told the frequency that we see from a cycle. In other words, how much of a cycle we get through in a particular amount of time, or how many cycles we get through in a particular amount of time. So right here, what we're going to do is take a look at some word problems. And we're going to start with the example of a weight on a spring. So we've got a weight on a spring, suspended on a spring, right? So it's basically at its equilibrium, or sort of at its rest, right? And in our word problem here, we're seeing a weight on a spring is pulled down from its equilibrium. So we pull that weight down from its equilibrium, where it's resting, and we then release it, right? And of course, what's going to happen is the weight is going to spring up and then go back down. And basically, we're going to see the spring go up and down between extrema, maximum distances from the equilibrium. And in general, what we're going to see is that spring go up and down, right? Going above and below its equilibrium, or the height at which it rests, right? Now, we're told right here that the weight oscillates up and down and completes one cycle in 3 seconds, right? So one cycle in 3 seconds tells us that we have a period length, a time period of 3 seconds with which it takes us to complete one full cycle, going from the min to the max and then back to the min, right? Now, in general right here, we're told that the weight has a maximum displacement of 7 centimeters from its equilibrium. So right here, we're basically seeing our weight go down 7 centimeters from the height at which it rests, and up 7 centimeters from the height at which it rests, right? Now right here, we can say that from that, we have the amplitude of the wave, right? So we can say we've got an amplitude here of 7 centimeters. Now, finally, what we're told is that we want to write an equation that models the displacement from the equilibrium, and we're going to let t equals 0 be the moment the weight is released, right? So if t equals 0 is the moment the weight is released, then we're actually starting at a min, right? We're starting at a most negative displacement from the equilibrium, right? And if we're starting from an extrema, then in general we can say that the cosine function is what we're going to want to use to model this cyclic behavior, this harmonic motion. And since we're starting at a min, we're going to model this with a negative cosine function. So in general, we're going to say that we're modeling this with a negative cosine. Now right here, we need to determine the B value. We got the A value. We know that the amplitude is going to be 7, right? We know that we're going to be a negative 7 since we're starting in a min, and we know we're going to be modeling with cosine. What we need now is that B value that we're going to get from the period, right? So right here, we're going to say that if a period is 3 seconds, we know that a period is always going to be 2 pi divided by b. And right here, what we can then do is solve for the b value, and when we do that, we get b equals 2 pi over 3. So right here, using all this information, our b, our a, and the fact that we know we're going to be a negative cosine function, we can say that this harmonic motion, which is going to be basically this weight oscillating above and below its resting position, is going to be determined by negative 7 cosine of 2 pi over 3t. And so that equation right there is giving us the harmonic motion, right, or the displacement of the weight from its equilibrium at any particular time t. All right, so let's take a look at this one. Right here we have a weather balloon gets caught on the end of a windmill blade. The windmill blade is 20 feet long and turns at 2 rotations per minute. The balloon passes 40 feet from the ground at its lowest point. Determine an equation for the height of the balloon where t equals 0 is the balloon at its highest point. So right here, a couple things we want to do is just sort of get an idea of the picture we're seeing with this oscillation. So what I'm going to do here is I'm going to draw this windmill. Here are the blades of the windmill. And right here, we've got our windmill and something like this. And we've got our weather balloon caught on one of the blades of the windmill at the end of the blade. And right here, we can go through and sort of mark off some length. So we know that the length of the blade is going to be 20 feet. So as the windmill rotates around and around, we can basically say that we're going 20 feet above and 20 feet below what would be the middle height of the windmill, which would be that height right there. Now that height is going to be 40 feet plus 20 feet, since basically we can say that the weather balloon is going to be 40 feet from the ground at its minimum height, right? So right here we can say that the equilibrium, or the middle height that our weather balloon is going to be attaining, is going to be 60 feet above the ground, right? Where the min is going to be 40 feet above the ground, and the maximum height would actually be 80 feet. Now, what this tells us is that we have an amplitude of 20 feet, and that we are going to be adding 60 feet to the equation with which we model the harmonic motion here to get the height of the balloon. Now right here, the next thing we're told is that we are rotating at 2 RPMs, and this is rotations per minute. So this is actually the frequency with which we are rotating. Right? We're seeing 2 full rotations of the windmill per minute. Now, we know that frequency is given to us in terms of units of time. So since we've got frequency with respect to units of time in terms of single minutes, we can say that we know that our frequency of 2 is going to be equal to b over 2 pi. And we can basically use this to solve for our b value, right? Now right here, we can say that with an amplitude of 20 feet, we have a equaling 20. We can say that when we solve for b with our frequency, we can say that we have b equaling 4 pi. And right here, we're told that we want to determine an equation modeling the height of the balloon, where t equals 0 is the maximum height, or the highest point. So right here, since we're starting from an extreme, we're going to use a cosine function to model this harmonic motion. And right here, we're going to say that that cosine function is going to be positive since we're starting at a max. And right here, we can say that the height of the balloon at any time t is going to be 20 times cosine of 4 pi t plus 60. And that would be the equation that models the height of the balloon at any time t.